Good afternoon, and pleasure to be here to discuss genomic risk through the lifespan, coming from Mass General and the Broad Institute here in Boston. I'll start with my acknowledgments. First, Mark Chaffin, a very talented computational biologist in our group, and secondly, Sekar Katharasan, who I just finished up a postdoc fellowship with in the last several months. And thank institutional support from both MGH and the Broad, and funding support, including from NHGRI. So, it's not a new phenomenon that family history associates with disease. In fact, there's a rich history of studying this issue for heart attack at my own institution. Some of you will recognize in this picture Paul Dudley White. He started our cardiology division over 100 years ago. And I recently went back and read one of his seminal articles published in JAMA in 1951. And here the experimental design was actually quite simple. He asked 100 patients who came to Mass General with a heart attack whether or not their parents had suffered a similar fate. And it turns out that a family history is present in about 27% of cases as compared to only 14% of controls. Now, this observation has stood the test of time, where we know that a family history is associated with about a twofold increase in risk of disease. However, it motivates a much more interesting question, which is what are actually the discrete DNA-based drivers that underlie this increased risk? So the traditional approach to DNA-based prediction has, of course, focused on monogenic mutations. And for cardiology, that really has, we've really thought a lot about familial hypercholesterolemia. Here's a situation where there's a rare mutation present in about 1 in every 250 individuals. It prevents clearance of cholesterol from the circulation, and over time, that increased exposure leads to about a tripling of the risk for heart attack. So there's a lot of work ongoing to actually find these individuals because we know that decreasing their cholesterol can help prevent onset of disease. But from a conceptual standpoint, how actually might someone's DNA predispose them to a heart attack at a young age, say by the age of 50? And it turns out there are actually two models. One is a monogenic model, such as I discussed, but the second is actually a polygenic model, which we've heard a lot about today, where it's not one mutation, but actually the cumulative impact of many variants scattered across the genome that in aggregate could increase someone's risk quite substantially. So we recently sent out to ask that question, and we said, can a polygenic score identify individuals with risk that's actually equivalent to these monogenic mutations, meaning a more than triple the normal risk? We did that by starting with just a list of 6.5 million variants, and they're from recently published GWAS, and used an algorithm to combine that into a single number. Now, this number is actually normally distributed in the population. So unlike monogenic mutations where you have one or you don't, by and large, this is actually a normally distributed curve with some people high and some people low. And what we observe here on the x-axis is the percentile of the polygenic score, and on the y-axis is just the proportion of the individuals who had heart attack by the time they had reached middle age. What you can see is that there's more than a 10-fold gradient across these percentiles. Moreover, if you look at just the tails of the distribution, what we observed is actually the top 8% of the distribution as compared to the remaining 92% had a more than triple the normal risk. This was risk equivalent to a monogenic mutation. Some folks have suggested we compare not to the bottom 92%, but the middle quintile. And in that analysis, the results were almost identical. Instead of 8%, it was 8.2%. Now, importantly, I'm showing you here the traditional risk factors of the top 8% of the polygenic score versus the remainder of the population. And what you can see is that there are subtle differences. For example, family history is present in 44% with those with high polygenic score versus 35% of the remainder, 32% versus 28% for hypertension, and so forth. So we see modest enrichment, just as you would expect, for all these causal and important risk factors, but there's no way I could pick out one of these patients if they came into my cardiology clinic without having access to their genetic information. So in summary, when we think about genetic risk for heart attack, again, as I mentioned, monogenic mutations are present in about 0.4% of the population, associated with a tripling of the risk for heart attack. In current clinical practice, we use LDL cholesterol as an imperfect but reasonable surrogate for the presence of these mutations. And we know that if we can identify these folks, we can markedly reduce their risk by LDL-lowering medications. What about polygenic risk? Well, here it's actually 20 times as common, 8% instead of 0.4%. Despite that, the odds ratio for heart attack is identical, again, a threefold increased risk. And these individuals are actually flying under the radar within our clinical practice. And we observe this both in the UK Biobank as well as in our own data from the Partners Healthcare Biobank of Brigham and Mass General patients. Moreover, if we were able to identify them, we have generated evidence that supports that these individuals benefit the most from medications, such as statin or cholesterol-lowering medications. And adherence to a healthy lifestyle has actually been associated with a normalization of risk, even among those with the highest polygenic scores. So we initially did this for heart disease, but in our paper we chose an arbitrary list of additional diseases to focus on, and included atrial fibrillation, as Patrick went into detail on, diabetes, inflammatory bowel disease, and breast cancer, which we heard about as well. And the take-home point is that this is really a generalized approach that works for any heritable disease, again dictated by how polygenic the disease is. But in each case, you can really identify some meaningful 1, 3, 8% of the population that is at triple the normal risk. And so we think this is actually an important foundational scientific opportunity to now figure out what we do with this technology. So that was basically data based on middle-aged individuals for heart attack and a range of diseases. But I also thought I'd explore really how does polygenic susceptibility play out over the course of the lifespan. So this is work we published recently where we made a genome-wide polygenic score for obesity. The technique was the same, took about 2 million variants, combined them into a single score, normally distributed, and tested the score in about 300,000 individuals from the UK Biobank. And we first said, well, what is the impact of this polygenic score on obesity in middle-aged individuals? Average age was about 57. And here I'm showing you on the x-axis the polygenic score decile, and on the y-axis is just their average weight in kilograms. And what you can see is there's actually almost a 30-pound gradient in weight across these deciles, and it was similar amongst both men and women. And in BMI units, there's about a 4.8 kilogram per meter square difference solely based on this polygenic score across these deciles. So this was, again, based on continuous numbers, but then we said, what about those who are most severely affected, the severe obesity, which is, as you know, associated with the worst outcomes, and is actually the most rapidly growing segment of obesity in our population. And here we saw an even more significant gradient where there was actually a 25-fold gradient across the deciles where there was only about a 0.2% chance that an individual was severely obese if they were in the lowest decile, as compared to about a 6% chance if they were in the top decile. So again, these were results in middle age, and we said, well, what if we go earlier in life? How does this actually impact risk in young adulthood, for example? And for this, we worked with collaborators at Framingham and Miriam Fornage from the Cardia study. We actually looked at about 3,700 individuals. Average age was 28. And these individuals, none of them were severely obese, but they were followed for an average of almost 30 years. And what you can see here on the x-axis, again, is years of follow-up, and on the y-axis is just the percent of them who developed severe obesity. And those in the light blue, again, were the bottom decile of the polygenic score. Only about 1% of them actually went on to develop severe obesity. So these individuals actually inherited inborn protection from this disease. By contrast, if you were in the top decile, about 16% developed severe obesity, and actually the majority developed less severe forms of obesity as they transitioned from young adulthood to middle age. What about even earlier? And so here we said, okay, well, what if we actually go to the time of birth? And what does the score tell us? The score can be calculated, of course, from the time of birth because it's a DNA-based test, but what does it actually tell you about birth weight, for example? And here we work with collaborators in the UK from the ALSPAC birth cohort. It was about 7,000 people. They recruited the pregnant moms, actually, and they followed the offspring from birth to age 18. And here I'm showing you again, on the x-axis is the polygenic score decile, and on the y-axis is just the weight in pounds. And what you can see is that perhaps there's a subtle trend at the time of birth, but I'm then going to walk forward in time and show you how this plays out as children start to age. This is 8 months of age, 18 months. Here's about 3.5 years where you really start to see a pattern emerge just as kids are starting to go into preschool. Here's 8 years, and here's 18 years. And so what you can see is that this genetic predisposition really plays out, and the gradient increases substantially as children age. And so it starts out about a 0.1 pound gradient at time of birth. And by age 18, we actually saw a 27-pound gradient across these deciles, which is actually identical to what we saw almost in the UK Biobank versus middle-aged people. Here the y-axis is weight, but we saw conceptually identical findings using instead z-score, which normalizes it to population norms. So again, this data really shows that one, that genetic predisposition to obesity can be quantified using a polygenic score that can be quantified at the time of birth. This score actually, the impact of it starts to take hold very early in life, even at the age of 3 years. We also showed that among those individuals who are the most severely obese in our society, the vast majority of them actually inherit a strong polygenic predisposition. And I think we always had a hunch that this would be true, but we now have evidence that we can quantify this in a meaningful way. And as a doctor, I think this actually could be quite useful because it really may help to destigmatize the condition in our society, because many in our society may say, oh, severe obesity is a disease of a lack of willpower, of inability to make good lifestyle choices. But here we actually confirm a very strong biologic predisposition amongst the majority of those who are most severely affected. Now, the flip side of that is also true, which is that DNA is not destiny. So some folks have said, oh, well, even in the highest decile, not everyone was severely obese. And I'll say first, I think that's not a realistic expectation for complex disease, that you would have a diagnostic that at the time of birth would perfectly predict your weight when you were 50, for example. But second, that's actually what's most exciting to me, because here we have an opportunity to say that you're at markedly increased risk. We can identify you early in life, but that lends itself to the development of a tailored intervention that may one day be able to offset that risk moving forward. So again, that was some of the work related to obesity. And I thought I'd share just a few slides on unpublished data, which is work put together by Sohail Zahid, a talented medical student in our group. And he was interested in thinking about polygenic susceptibility to Alzheimer's disease. So this is not, obesity is more or less a disease of young adulthood and middle age for the most part. Alzheimer's disease, of course, is primarily a disease of the elderly. And so he turned the same crank, made a polygenic score for Alzheimer's disease with a few million variants. And he looked first, again, in the UK Biobank, and he said x-axis, just polygenic score decile, and the y-axis is the percent of individuals who had been diagnosed with Alzheimer's dementia. And what you can see is first that the prevalence was low across all the deciles as expected. The average age was in the 50s. But the highest decile compared to the lowest decile, there's about a 5-fold gradient in risk. Now, some of you may know that Alzheimer's disease has a unique genetic architecture where the ApoE locus is known to be quite important, especially the ApoE4 variant. And so he actually looked at this directly and found that about 70% of the predictive value was actually dictated primarily by that well-known ApoE4 locus. But it's also true that the remaining genome-wide set of variants did contribute about 30% additional predictive value. So again, this is a situation where Alzheimer's disease is actually not as polygenic as BMI, for example, where here you actually are able to capture a strong locus with meaningful impact on disease. So that, of course, data was looking at everybody across the population, but he then said, okay, well, how does this risk actually play out? This was cross-sectional data, but how does this risk play out as people age? And so here I'm showing you just the 3 dots represent the 45-year-olds in the population. And what you can see is that almost none of them had Alzheimer's disease diagnosed, as you might predict. But he then went forward over time, and what you can see is that at 60 years old, you start to see a pattern, and really by the time folks get to 65, you see an exponential increase in the rate across all deciles, but you also see a clear separation for those in the highest decile of polygenic score. And the expectation is these curves will really continue to diverge if we had access to additional longitudinal data. So I'll note that there's a marked difference, especially as people reach 65, but also that even among the 65-year-olds with the highest polygenic risk, the prevalence was only about 1%. So what about the remaining 99%? And so here he thought to look at actually a marker of cognitive function. And so we looked at a test pretty well known in the cognitive field, which is digits remembered. So for example, if I recite my 7-digit phone number and you can spit it back to me, that's about average for most people. And so that's a digit remembered score of about 7. If you can do it with the area code, then you get a score of 10, for example. And so they actually did this in pretty much all of the participants in the UK Biobank. And again, what you can see is that in 45-year-olds, they were all pretty similar. But then when he followed them forward over time, you can see that everyone started to drop off, maybe unsurprisingly, but also unfortunately. But everyone started to drop off as they age from 45 to 65 on average. But those in the highest polygenic score decile really started to drop off quite a bit more substantially. And so here, I think, is an example of a situation where we now have a polygenic score that can identify, let's say, 1% of the population with 5x, 10x the normal risk. And then the question is, how could that be useful? And I would say it can be useful in a couple ways. One is that there's clear advantages to identifying people who are asymptomatic but are at very high risk versus very low risk based on genetics. So he's actually already done this using proteomics analyses, where he actually nominated confirmed known biomarkers and nominated new biomarkers simply by looking at the extremes of the polygenic score. And for a disease like Alzheimer's, where there are essentially no circulating biomarkers for the disease, I think this approach could actually be quite important. Secondly, most folks most experts in the Alzheimer's disease space look at just a plethora of failed clinical trials, and they say, well, why did it happen? Because the biology seemed pretty sound, and the leading hypothesis actually is that we're getting to people too late. So the clinical trial may have worked, it may have been an effective therapeutic, but the plaques are too far developed, and if only we were able to start earlier, maybe we would be able to show an effect. And so here I think there's a situation, I think Eric Boerwinkle mentioned this on one of his slides, where if you enrich a clinical trial for people who are at 10 times the normal risk based on genetics, it's really possible that you might have enough incident events to detect a difference and have a reasonable number of people in the trial, but also have enough of a enrichment that you might actually be able to show a difference. So here again, the use case for the polygenic scores, I think, will vary quite a bit across individual diseases. So I conclude here with just a statement of fact, I think, which is that polygenic scores enable genome interpretation, which I think is a growing field from the time of birth for a range of important diseases. And for a number of reasons, they will continue to improve quite significantly, I think, in coming years. And my goal is really to use this observation as the foundation for a career where we really think about how we use this possibility to not only identify these high-risk individuals, but ultimately disclose the risk and hopefully intervene to decrease the risk of disease developing before it ever happens. So let me stop there and hopefully have about 2 minutes for questions.
David.
That was great, Amit. Can you tell us a little bit about the relationship, in your studies at least, of polygenic risk score to family history?
Yeah, so family history, as you know, is a combination of really shared genetics and shared lifestyle, but you can't actually disambiguate which of it is for any given patient for the most part. And so in every polygenic score that we've looked at, there is a difference in self-reported family history between those who are high versus low, but the difference is actually quite modest. So it definitely provides incremental value over and above family history. So for example, for heart attack, I think the numbers I showed were about 44% of people reported that one of their parents had coronary disease if they were high versus 35% if they were not high. So the difference is there, but it's actually quite modest.
And this is fascinating, Amit. Thank you. So quick question about the analysis you did, choosing a threefold increased risk as a comparison for monogenic. That threefold, you did it for heart disease because of FH, but then you did it for other diseases. So a threefold increased risk for a common disease like heart disease is not the same as a threefold risk for a rare condition. So what was the rationale for that threefold increased risk?
Well, I'd say first, I think, again, we focused only on common diseases for this analysis, but I would say that actually across a whole range of diseases, the evidence is really emerging that even these monogenic mutations are not as penetrant as we actually thought. And so a threefold risk for familial hypercholesterolemia mutations is pretty consistent with what Mark and other folks at Geisinger have published, we've published. Even BRCA1 mutations, it looks like from both the UK Biobank and Geisinger data, it looks like the odds ratio is closer to 4-5 maybe, rather than something much higher from older literature. And so I think that the choice of those numbers was really motivated by what's been observed from monogenic mutations for common diseases. But even more important than that, we just thought it was a useful framework where if you talk to a medical geneticist, they'll say, oh, well, finding people with BRCA1 or LDLR mutations is quite important because they're at, regardless what it is, let's say it's threefold, maybe it's sixfold increased risk. And so we said, well, can you actually get there with a polygenic score? And it turns out you actually can for a meaningful number of people.
Steve?
I mean, I want to follow up on this point because I have to disagree with, for instance, the comment you made about BRCA1 and 2, because the population-based sequencing is different than coming into a cancer clinic, than being in a family, and depending on what the family load is. And I think the danger that we fall into is talking about, when we're talking about highly penetrant mutations, is genes as opposed to the specific mutations. So you look at BRCA1 and 2, just thousands of variants across that, and they have very different effects. So putting them all together is a very difficult thing to do. I mean, because we don't know what the average effect of BRCA1 is in the general population. We certainly see the Ashkenazi 185 at a certain rate in people of one background and as opposed to another. But when you start modeling this and you bring in the rare variants, I think this is where we have to be really careful that we're not, for the polygenic risk score, I get that because everything is 1.1, 1.05, 1.07, give or take a little bit, and so you're in a better space to do that. But I think we have to be really careful about over-interpreting genes as opposed to mutations when it comes to rare variants.
Yeah, I totally agree that as a field, we're really struggling with how to annotate rare variants and distinguish ones that are pathogenic versus not. But again, this is not my work, but the work of folks at Geisinger, where they actually went through tens of thousands of exomes, actually annotated using the clinical standard to say what's pathogenic or likely pathogenic using ACMG criteria, and they actually aggregated those variants together in a group to get at some of those odds ratios.
But you have to go to Enigma, not to ACMG, I mean, for the actual variants for BRC, for instance. And that's where you need family history and a lot more information to be able to interpret those things that looked at. I mean, you saw this very nice paper, of saturation genomic editing, by Jay Shinduri, and it correlated fairly well, but it wasn't picture perfect. And I think, we have to be really, really careful about lumping too much of the rare variants together. The SNPs, I have no trouble because we don't understand how most of those work at this point.
Mark?
Yeah, so since it is our data, I'll just weigh in. I think we are transitioning, right?
Are we? Does that mean that we can tell Dr. Khera that he can take his seat?
Thank you.
Thanks.
Yeah.